Okay, so first, have a pencil handy. Got it. All right. I deliberately am not going to give you any information yet, because probably the most important step of this whole thing is this process at the beginning. We have to have a plan of attack. If you just start, say, combining resistors in series or combining them in parallel, just doing stuff and writing stuff in the margins and whatnot, you're going to end up being confused and not be able to finish the problem. You might be able to find the equivalent resistance, but you won't be able to work backwards, which is the hard part of this. So let's have a plan together. And by that, I mean, let's draw out what our first line of attack will be. For example, when I look at this, what part of this circuit do you want to combine first? That's what you ask yourself. You can also ask yourself, what's the overall structure here? That's a little harder to see with this one. It's going to end up being series, I think, but I'm looking at these three. I think we can combine those. Now, when I say combine, does that mean we always just add them together? No, it depends on whether they're series or parallel. So, since that's going to be my plan, what I'm going to do first is I'm going to draw, so this is my voltage, high potential, and I'm going to take those three and combine them into one equivalent resistor. And I'm going to call that resistor R1/2/3. That's my notation. I don't know, what Sal does or somebody else, but this is going to be my notation. This is going to be the combination of these three parallels. I'm going to draw the rest of the circuit. This is why patience and willingness to use a little bit of paper here is important, because if you try to do too much, when you go to work backwards, it's going to really confuse you. So patience is important here. Delta V, this is still R4, this is still R7. And you can see both of those. This is, but you have it in front of you presumably, this is still R6 and this is still R5. So my first step is to combine these into one equivalent resistor. And we'll talk about how to do that later. Now what do we want to combine? I'm going to attack these two, I think. Don't you think? Yeah. All right. So I take my time. And even though it's a little tedious to do it this way, you're going to thank yourself later. I redraw the circuit. Let's see, and label it. This is R1/2/3. R4 hasn't been touched. I'll put it over here, R4. And now, over here, oh, you can't see that. Thanks for telling me, guys. All right, so, and over here, what do I have? Using my way of doing things, what would you call this? R5/6, right? And we know that since they're in series, all we're going to do is add those two together to get this. But we'll get there. What would you do next? I'll pause. Well, if you're watching the video, you can pause me as well, or speed up. I'm going to wait because I'm doing this during class. But ask yourself, what part of this would you attack next? Yeah, I would look at these two. So I think we can look ahead a little bit now. We're going to end up with a series circuit. This one is going to be in line with whatever these two are combined, and then in line with R7 down here. I'm going to have that. I'm going to use all the paper at my disposal, so I'm going to flip my page here and do that next one. So for that one, I'm going to have voltage, and it's going to go to R1, 2, 3. And then it's going to go to the combination of, this is interesting, this is going to be R4, 5, and 6, but it's all said and done, right? and then R7, and back to the voltage. Now we're one step away from getting the equivalent resistance. And what that is the voltage source doesn't have eyes. It just senses a resistance. It doesn't know how that resistance is made, what combinations. It just senses one resistance for that circuit that produces a current going through the battery. So we can boil that use our knowledge of how to combine resistors to find that one equivalent resistance. And in this case, the last step is we're going to just add these three together because they're in series, and the circuit's going to look like this. So our end result is to always end up with a single circuit or a single resistor in the circuit. And we call that the equivalent resistance, EQ. All right, so we're here. It's at this point, I'm going to start doing this. I'm going to point out that every resistor, fictional, right, because we added up to get this one, but every resistor in our diagrams has a current going through it, an I, and it has a voltage drop across it. So the voltage here will be higher, and then after the current flows through, it'll be lower. Think of it like a waterfall. That's the best way I can describe it. Okay? Now, for this really simple circuit, we'll calculate this in a minute. This voltage drop is the same as this because there's only one resistor, right? If this is 100 volts, then all 100 drop here by the time you get back to this, right? So I know this, at this point, is the same as the original. I can calculate this if I know Ohm's Law. And I want to point out that in every one of our other resistors, like R7 here, R7 also has a current running through it, we'll call I7, and a voltage drop across it called delta V7. So every one of these resistors, real or made up, so to speak, has its current going through it, so current 456, and a voltage drop across 456. And basically, we're going to work backwards and fill those in as we go back. And I'll explain how to do that. But let's get this equivalent resistance because it all hinges on that. So, how do we get that equivalent resistance? We'll go back. We got our map here of what we want to do. So we're going to, let me back this out a little bit so we can see two. So, we combine these first to get R1, 2, 3. These three are in series or parallel? Parallel. So we would have done it by doing 1 over R1, 2, 3 is equal to 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. Parallel, it's a 1 over formula. And it's about this time that I should probably give you some values. So let's make up some numbers, shall we? Let's call this 12 volts. Resistance 1 will be 7 ohms. Resistance 2 will be 6 ohms. Resistance 3 will be just 2 ohms. And I'm just making these numbers up, by the way. Don't panic. Let's make 4 8 ohms. go 5 will just be 3 ohms. 6 will be 4 ohms.
Is 3 a 7 or a
2. 2. My apologies. And 7 will make, let's make 7 9 ohms. Keeping the numbers simple. Resistances are often not that small. Like they're usually hundreds. There's mega ohms. You know, depending on what you want to do with them, they're not usually in the single digits, but it helps for our purposes. Okay, so take a moment, try to work ahead of me. Grab a calculator because it's going to be a lot easier with a calculator, and let's see if we can calculate the equivalent resistance for this one. If you're not sure how to handle that formula, let me get my calculator out. Then watch what I do, and I'll show you how to do it. We don't need to find common denominators and all that crap. So we have, this is going to be 1 over 7 plus 1 over 6 plus 1 over 2. You can literally, to get that, you can literally type it like you see it. So for example, I don't know if you can see my calculator as well, we'll see. You can just type 1 divided by 7 plus 1 divided by 6 plus 1 divided by 2. Another way to do it would be to type in 7 and then do to the negative 1, the inverse key. It's the same thing as 1 over. So I could do 7 to the negative 1 plus 6 to the negative 1 plus 2 to the negative 1. That's the same thing. I'll press clear. I'll do it the way I was doing it earlier. Plus 1 divided by 6 plus 1 divided by 2. Now, here's the danger when you're doing parallel. You hit enter, and you think, that's my answer. But that ain't your answer. That's 1 over the number you want. So you can't forget that that's still upside down. So 0.8, I'm just going to call it 0.81. This is not the resistance, it's 1 over. We need to flip that right side up. So you can do it a lot of different ways. Once again, the x to the negative 1 key is probably the best one, or your calculator may have a 1/x key, same thing. If I flip that right side up, R123 is about 1.24 ohms. A quick note to help you keep things straight, or to check your work as you go. When you do this 1 over formula, your answer should always be less than your smallest number, or your smallest number resistance in this case. So my answer should have been less than 2. If it came out to be more than 2, I'd know I made a mistake. Right. You'll never have an answer when you do this 1 over formula that's bigger than your smallest number. So this resistance is 1.24 ohms. And while I'm here, I'm also going to write down that at some point we're going to want its current and its voltage drop. We'll come back to that later. But I just put places for both of those up here. All right, so now in the next step I combined 5 and 6 to get this. But the beauty here is that they're in series. How do I combine those? Resistor 5, 6 is just going to be the resistance of 5 plus the resistance of 6. When they're in series, you just add them. So 5, 6 is just going to be 3 plus 4. 3 ohms plus 4 ohms. So resistor 5, 6 is 7 ohms. And I'm going to squeeze that in here. So resistance for 5.6 is 7 ohms. I'm also going to later find its current, and I might as well make its voltage drop as well. And I just put spaces in there for those as I go along. We'll fill them out on the way back. All right. If you need to pause the video while you're getting caught up, feel free. But my next attack is going to be to combine, I believe was to combine these two, which are in parallel. So, to get that resistance, let's see, I'll try to squeeze it up here. Since they're in parallel, it's a 1 over. So the combination of 4, 5, and 6 is going to be equal to 1 over the resistance of 4 plus 1 over the resistance of the one we just found, 5, 6. And that's going back to, and this requires page flipping, we are combining these two, which are in parallel. So that's why I have to use this equation. So that resistance, 4, 5, 6, is going to be 1 over the resistance of resistor 4, which is 8. So 1 over 8 plus 1 over 7, if I remember correctly. I did that wrong. There we go. And then I flip that number right side up, so I have 1 over our 4, 5, 6. I don't usually write this step, but just to make sure that everybody knows what's going on. And then I flip it, and I actually get a resistance. Sorry. Notation's a little wrong. R 4, 5, 6. A resistance on that one of 3.7 ohms. So I'm just going to jot that down here. 3.7 ohms. A little messy, but just to separate how I got there and what my results are, I'm going to put a box around that. And while I'm here, what was this one? 1, 2, 3 was a resistance of 1.24. And resistor 7 was 9 ohms. And so I'm now have 1, 2, 3 in series. So the good news is that's pretty straightforward. We're just going to add those 3 together. So the equivalent resistance for the circuit is going to be R123 plus R456 plus R7. That's going to be 1.24 plus 3.7 plus 9. So I'm down to 3 resistors. By the way, if you didn't draw out each picture, you'd be baffled by now as to what the hell you're doing, right? You'd be like, where am I at? What? So drawing these circuits out, these different circuits out first to represent each step along the way is going to help you. It's like leaving breadcrumbs if you're trapped in a maze, which happens to everybody all the time. So you know what I'm talking about.
You add all 3 of the circuits together?
All 3 of these resistors, yep, in this one right here, get added together because they're in series. And I'm going to add them together with a calculator because I'm lazy. 1.24 plus 3.7 plus 9. All right, so for the entire circuit, I got an equivalent resistance of 13.9. I'm rounding for ease of working with the numbers. At this point, you're going to start using Ohm's Law to the point where you're tired of it. You're going to use Ohm's Law like all the way back. So it's probably a good idea here early on to make sure we know what Ohm's Law is. Ohm's Law in your equation, on your equation sheet looks like this. It gives you the current is voltage over resistance. Of course, if you need voltage, it's just IR. And if you need resistance, which we won't need, right? We have resistances all the way back, but sometimes they'll ask you for a resistance. That's voltage over current. All of those are Ohm's Law. We are going to use basically these first two ways of looking at it to find voltages and currents as we go back. So let's start with this really basic circuit. We have one resistor, 13.9 ohms. I've given you the voltage drop for the circuit, which is what? 12 volts? Is that, all right, so delta V is 12 volts, and since there's only one resistor, the drop across that resistor is also 12 volts. Can you find the current in this simple circuit? Well, right, 12 divided by 13.9. 0.86. So I have a current of 0.86 amps. Remember, it's amps. What's important about that current, or another way of phrasing that current, is that will always be the current, we would say, that passes through, kind of through the battery, if you know what I mean. Like, no matter where I go, I call that the overall current for the circuit. And another way of describing that is the current through the battery. Because later, it might split into branches, but it's always, the total current's always got to be whatever this value is, 0.86. I'll let you get caught up, and then I need you paying attention because this next part is probably the most important part. Now, listen on this one. So you can just listen to this. I mean, if it helps you to take some notes on it, but all right. So we're going to work our way backwards. So we have a bunch of resistors, for example, that we've combined. All right, R123 or R456 or whatever. That's represented here by R combo. If you look back, you go back up your chain of circuits, and you look, and you're looking at how did I combine them? Were they series? Were they parallel? Right? Here's two examples. So here I have this combo one, and before it was, turned out that was a parallel one. For this one, for this example, it was series before. The key here is this: voltage and current. For one situation, you can, whatever the current was going through this one, you can bring it back. For another situation, whatever the voltage is the voltage for all of them. So this is the part that you want to kind of, I guess, memorize, for lack of a better term. If they're in series, what is always the same for things in series? Is it voltage or is it current? All right, current's always the same. So if your combo, if you go back, whatever the current was here going through the combo one is the current going through. So the current here in your combo is the same. Everybody has that same current. Cool? So going back, you want to remember, you can bring the current. The voltage here, this delta V for the combo, is not the delta V for each of these. It's actually going to be V1, V2, V3. When you add them up, you'll get your voltage for the combo. But they're not the same as the voltage here. The current is. So if you go back to series, bring the current with you. Cool? Everybody gets that current. So if you go back to parallel, so if I know the voltage drop across this is delta V combo, whatever that is. If I know it's, I'll even use a number here. Let's say I know it's 17 volts in this situation. Then what's the voltage drop across this one? 17. What is it across this one? 17. So everybody gets that. You can bring the voltage back. So if it's parallel, bring the voltage with you. Cool? that is what I would want you to memorize. I'm going to add on to that a little bit to help you understand. Let's say the current going through here was, I don't know, 20 amps. That means 20 amps of current came up to this junction. And 20 amps of current is leaving that junction. But do each of these get 20? If a river comes up, right, and splits, you have to divvy that up. So current gets divvied up. This would have this current 1, current 2, current 3. But what do you know about those 3 currents? They got to add up to 20. Okay? Right now, here's the thing. More current will go through the least resistance, that whole path of least resistance. And we'll see that as we go through. But it's just important to know, really, that it's going to split. And that those sums are going to add up to 20. Voltage drops here. So if your waterfall went from, let's say the voltage drop here was, let's call it 20, no, don't confuse them. Let's call it 30 volts. So in other words, you went from 30 volts down to 0, or you went from 60 to 30, right? It doesn't matter, right? Because it's voltage difference. Right? But if your drop is 30, we'll keep it simple. This is like an imaginary giant waterfall, dropping 30 feet. This is really, then you find out, oh no, it's not one big waterfall. Each one of these is its own little drop as you go down. So if this one is 15 volts worth of drop, and this one is, let's be simple about it, shall we? This one's 5 volts worth of drop. How much do I have to have here? I gotta have 10, right? So that the 3 of them add up to the voltage drop. That's a little extra. What you want to lock into your memory is if I'm going back from a combo to a series, the currents are all the same. If I'm going from a combo to a parallel, the voltages are all the same. And that's all you're going to need, because Ohm's Law will get you the missing pieces. All right, so let's see that in action. So, going from here, my equivalent, to the circuit before, am I going to a series or am I going to a parallel?
Series.
If you look at going to series, so what can I carry? What's the same for all of them then? All right, whatever the current was back here. So I now can write I, 1, 2, 3, is 0.86 amps. And I can write I, 4, 5, 6 is 0.86 amps. And I can write I7 is 0.86 amps. I can bring the current back. So that means that, I'll call resistance pink. That means for these, I know the resistance for every one of them. And we figured that on the way. I now know the current. Current reminds me of water. So I know the current for all of them now. So I can use Ohm's law at each place to find the voltage drop across each. And what do I know about if I find the voltage drop here, here, and here, what do they got to add up to? They got to add up to that total, the 12, right? In this case, because that's what I had. So let's figure out that voltage drop, shall we? So the delta V for resistor 1, 2, 3 is going to be I times R. It's going to be those two multiplied times each other. All right, using this form down here of Ohm's law. So for each of them, I do I times R. I got 0.86 times 1.24, and it drops 1.1 volts. Notice, it's a tiny little resistor. It does not dissipate a lot of energy. You do not lose a lot of voltage, just 1.1 volt. Where's the biggest drop going to occur? All right, whichever one has the biggest resistance will have the biggest drop. All right. So let's do this one right here. It's going to be 0.86 times 3.7, 3.2 volts. And here it's going to be 9 times 0.86, 7.74. And we figure that out for all of them. I will now put the voltage drops in yellow. I can still write that if I need it, the current through the battery here is the 0.86. And the overall voltage drop, of course, is 12 amps, so 12 volts. Now, just out of curiosity, what do our voltages add up to? 1.1 plus 3.2, that's 4.3, plus 7.7, this comes out to be 12, right? All right, so good. We're in good shape so far. All right, then, where are we going back to next? I got to go to the back page, so it's going to be a little tricky. So, which one did I do next? I combined 4 and then 5 and 6, that one. So this one right here. Sorry, this one right here. This is my combo. If I look back, what was it before? It was parallel, right? So what am I allowed to bring? Voltage. So right away, first thing I do is I write down the voltage for each of them. And I go back, what was it for their parent, so to speak? All right, the voltage drop across that was 3.2. So that's what I bring back. Cool? All right, that's where I get that information from. So the 3.2 comes back here. Voltage, 3.2. Let's see, I got R4, I got delta V4, and I got current 4, and I know this is 3.2 volts. Yeah, sorry, my fault. How's that? Better? All right. If I want, I can also, I should probably just bring along the other stuff real quick. This was 1.24. Delta V across 1, 2, 3 is 1.1 volts. And the current hasn't changed going through that. So that's still 0.86, is that correct? 7 was 9 ohms. Voltage drop was 7.7, and the current through 7, I'm all the way down here where you can't see it, is, he goes back, he looks, 0.86 as well, yeah. I just bring that information with me, but the key is I can only bring back, for the one I separate, I can only bring back the voltage because it's parallel. I got to use Ohm's law to figure the current. By the way, R4 is 8 ohms. So I'm going to use Ohm's law, or the version that says I is delta V over R. I'm going to use that to find the current in both of these. So for example, for resistor 4, I'm going to go 3.2 volts divided by 8.4. So I got, that makes sense, 32 divided by, so 0.4 amps. And I can use Ohm's law here too. Or, what do we know these two currents have to add up to? If 0.86 went into this branch, right, and 0.86 came out, these two better add up to be, the two currents better be 0.86. So if you do Ohm's law, double check it, but I'm guessing this is going to be 0.46. So, and I would get that by doing 3.2 volts divided by 7, and with rounding, yeah, 4.46 if you round it. So there's a quick check you can do on yourself. So I got, I hope I color coded them the right way. Voltage, current, resistance for this one, and I have resistance, current, voltage here, and so on and so forth. I think this is the one I'm concerned with now, aren't I? Because going from here to the next one, yep, this stayed the same, no big deal. But this is the one that's the combo that I'm now breaking apart. And I'm breaking it apart in series, aren't I? All right. So I don't have a lot of space over here, but in this case, I'm going to get rid of this stuff because we already did it. That's the other thing. I don't know why people work in pen, but okay. So I got current through 5, resistance through 5, delta V through 5. I got 4 is already done. I could just transfer all that information up there. 6 is the other one I got to worry about. I got resistance through 6, current through 6, voltage drop across 6. All right, so what do I know? Well, I know the resistance is already. 5 is 3 ohms. 6 is 4 ohms. What can I bring back from their parent? All right, since they're in series, I can bring back the current. That's going to be 0.46 for each. And then I use Ohm's Law to find me the voltage drop. And voltage, Ohm's Law in this case, delta V is IR. Multiply the 2 to get the voltage drop. So for 6, it's 1.84 volts. And for this, it's 1.38 volts. And you can always check yourself. Do those two voltages add up to 3.2, what we had before? Yes. So we're in good shape. So let's do this, both in class and on the video. See what you can do. I don't have a ton of space up here for this one up here. Let me make this bigger. There we go. For this last step, from going from this combination to these 3, not a lot of space for me to write it. Try to find the resistance, obviously, which you have, the voltage drop, and the current through each of these 3. And I'm going to pause what I'm doing, and when you come back, so pause your video. When you come back, I will tell you the answer, and we'll see if you're right. So as an intermediate step, just pointing out that since we're going back to parallel, the voltages are what we carry back. The voltage was 1.1 volts for this combo, and it's now, so that same voltage drop is going to apply to every one of those. So check your answers. This is what you should have, but I want to point out something here. So the current that comes in is 0.86 amps. That current has to split 3 ways, but it doesn't split evenly. It doesn't split evenly. More of it is going to take the path of least resistance. This is an easier path for the electricity, so more current goes through there. So I3 down here, 0.55 amps goes through there. Only 0.18 goes through here, and even less, 0.16 amps goes through here. But you'll notice, as long as you account for rounding, 0.16 plus 0.18 plus 0.55, it gives us, there's a lot of rounding that goes on there, so I'm pretty sure that's why it's not exactly the same, but you get the idea. But it's important to note that it won't just split up evenly because there's 3 paths. The electricity can sense. It's more complicated than I can tell you right now, but basically as the electric field goes out and senses which path has the least resistance, and more of the current is diverted that way. But it all comes back and leaves at 0.86. And the voltage drop across it is the same for everybody. If you put a voltmeter on either side, it would read 1.1 volts. And if you put it across here and here, same thing. Here and here, same thing. Or over here and here. All right, here endeth the lesson. Oh, wait, not quite, actually. Third period, pay attention to this as well, by the way. You'll notice at the end, I want you to find, you can write down the various resistances and voltages. I also ask for the power dissipated in each one, but just remember, power is I times V. So you just simply, to get the power, you'd have to multiply I times V. All right, you can find the power dissipated in each. For the whole circuit, we could say, let's see, for this one, it was 12 volts. The current through the battery was 0.86. So you can multiply those two to find the total power dissipated in the circuit. All right, there it is. Now end of the lesson.